I propose MHEX, a scalable and general module to improve the explainability of AI. And before we dive into the details, let me quickly walk you through the main topics we'll be covering today. And our discussion will start with the importance of explainability and followed by how we can explain AI's results. And we'll then look at how MHEX helps us to explain the finer details of AI decisions. And next, we'll explore results from computer vision and NLP, and how global and local analysis help enhance the explainability of MHEX. And we'll also discuss the implementation of MHEX, and then get a conclusion. Let's do it. Explainability actually plays a crucial role in AI today. And for example, when a bank uses AI to make decision about loan approval, we need to be sure that the decision is based on relevant factors like financial data, not things like skin color or gender. Or when AI is driving a car, we need to know what it's focusing on. Is it looking at the road, pedestrians, traffic lights, or maybe just the sky? And just like when a doctor uses AI to help with diagnosis, both the patient and the doctor need not only the result, but also an explanation of how those results were reached. Before we dive deeper into explainability, let's first take a look at how AI actually recognizes things. For example, when we look at the picture of a dog, we usually notice the overall shape first, and then we pay attention to the details like fur, ears, nose, and mouth. But AI works in a different way. It starts by picking up the small details first, like edges, textures, and patterns, and then it combines all of these bits together to form a higher level understanding of the object. So the process looks something like this. AI starts by gathering small details from the image, like edges, and colors, and textures. Then it gradually combines these details to extract higher level semantic information. And step by step, the AI builds up its understanding of what it's looking at. And finally, it reaches a decision. It's a dog. So the AI has correctly identified the image as a dog, but that raises an important question. How did it make that decision? And can we understand the reasoning behind this? The answer is yes, we can know the reason somehow. We use the technique called GrandCam, which helps us to see which part of the image activated the neurons in the AI the most. And as you can see here, the model is focusing on the two big ears, which makes sense for identifying a dog. And GrandCam is just one of many techniques we can use. For example, there is GrandCam++, which improves on GrandCam by using second derivatives for even finer insights. And there is also SHAP. This is a method based on Shapley values, which is an approach that actually won a Nobel Prize. And we can notice that this method gives us a rough idea of which part of the image are important. But can we go even deeper? Can we understand the finer details? That's MHEX's job. As we mentioned before, we know that the details are processed in the early stages of an AI model. So is it possible to uncover that what the AI is really seeing and those early layers? To achieve this, we need to introduce a method called deep supervision. Essentially, deep supervision forces the early layers to give their own predictions instead of just passing information to the next layers. And of course, the early stages are not 100% sure about their answers. And this stage, they don't see the whole picture yet. They are just picking up on small details, right? But that's exactly what we want. We need these early layers to focus on the details that really matter for figuring out the final answer. Here's a real example from ImageNet. As you can see, the salience map from the early stages are really detailed, and they highlight specific features like the spots on the leopard's body and even the leaves on the tree. But as we discussed further, these early layers are not very confident about their predictions because they only see small details. However, as we move deeper into the layers, the salience map become more refined and start to focus on the bigger picture. By the time we get to the final layer and everything comes together and the AI is confident about its prediction, it's a leopard. And we can sum up all these stages then to get a clear, detailed final explanation. So why do we need details from the early stages of AI? Just take a look at these medical images. These are pathology images, and they are absolutely packed with fine details. For example, the disordered cells and the black spot are indicators of cancer, and the long fibers and the nucleus can reveal smooth muscle tissue. And we can identify the lymphocytes by the dense cluster of small round spots. Let's check MHEX work. I think it works well and it has highlighted all the details like the cells, fibers, and the spots. And MHEX is really sensitive to the fine details that are so important in medical imaging and helping us better understand what's going on the micro level. Now let's talk about the NLP side. And transformer-based model like BERT are incredibly important these days. In fact, the T in ChatGPT stands for transformer. And these models are amazing at handling language process tasks. Here we have examples from news classification task, which distinguishing between business news, sports news, and other types of news. Our goal is to understand why the AI classified a piece of news as business or sports. But there is a challenge with transformers called over-smoothing. And this happens when every word pay attention to every other word and, uh, and aggregate repeatedly across layers, making the information so evenly distributed that we cannot know which words were actually important, as shown in the rollout results. And MHEX handles this problem well because the, its early layers don't suffer from over-smoothing. Instead, it extracts the fine-grained details. For example, in business news, MHEX highlights keywords like oil prices, surged dollar, inflation check costs, and in comparison, SHAP, which calculate Shapley values by perturbing words, it seems to struggle with showing the same level of detail, which while Shapley is a powerful tool, but in this case, it doesn't highlight the important words as clearly as MHEX does. And we can see that MHEX did a great job But there is still one more challenge we need to address. As we mentioned before, the early stages of the model are not very confident about their predictions or series maps. And this means some of the features they highlight might be uncertain. So the next step is to work on excluding these uncertain features. First, the AI processes the image of the dog into something called an activation. Or you could think of it as a vector that represents the features it has been identified. And next, we apply a ReLU function to this vector to make sure all of the features are non-negative. And finally, we connect each dimension to the neuron by a fully connected layer. Once we ensure that every feature is non-negative, using a ReLU, we can analyze the corresponding weights of the neuron. The idea is straightforward. Positive weight means the feature contributes positively to the neuron, and while negative weights means it has a negative contribution to the prediction. What we do is simply block the negative contributions and leaving only the positive features to influence the final salience map. And this helps us refine the explanation and focus on the features that truly matter. Because this is a fully connected layer, so every feature is connected to every neuron too. And this means that each feature could potentially contribute to multiple neurons. But our goal is to figure out which features are most devoted to specific neurons. In this case, we can see a feature contributes only to the dog neuron, and that's exactly what we are looking for. With features like that, we can definitely form a clear salience map which focusing on dogs' characteristics. For features like these, some of them might seem hesitate or include common traits or even noise. Let me explain. Take this feature as an example. It might not be entirely sure about its contribution because maybe it contains something common like fur. Like birds, dogs, and cats, they all have fur. So it's not very specific to a single class. Now, consider this feature. It might include noise, like parts of the background which don't contribute to any of the neurons. And these kinds of features can distract the model from focusing on what really matters. What we do is to block them and to make a clear salience map. And here are some examples that show how the salience map from early stages become gradually clearer as I applied the analysis. From A to C, we can see the background gradually faded out. Now let's dive into the core component, MHEX. And this part could be a little technical, but bear with me, please. It's important to understand how it works. And on this slide, we'll discuss how MHEX is integrated to ResNet. So ResNet uses something called residual connections, also known as shortcut. And these connections allow information to skip layers and flow through the network more efficiently. And MHEX takes advantage of these residual connections by deploying within them. In this way, we can integrate MHEX into the network without disrupting its original architecture. So what exactly does MHEX do? MHEX takes two inputs, the inputs of the block itself and the output of the block, and which we call G, or the global information. Then MHEX produces two outputs: the enhanced activation, which is passed down to the next layer, and deep prediction, which we use to calculate a loss. And this loss helps us to helps guide the early stages of the network to focus on details that which are relevant to the final answer. And by this way, we make the early layers of the network more sensitive to the details and improving both explainability and performance. As the UML package diagram shows, I added MHEX to every residual block in ResNet. And in the networks like BERT, the transformer encoder also has residual connections, similarly as ResNet. And I applied this the same approach to it, but don't forget the layer norm module. And actually, it is not necessary to deploy MHEX in all the residual connections. For instance, in the news classification task, I only use the first three MHEX modules for the salience map due to the over-smoothing problem. All right, let's switch into dark mode for this one. What you see here is the actual implementation of MHEX, and we'll break it down step by step. As the Python code shows, first, MHEX starts with two inputs, the block's input and its output. And then we apply global averaging pooling to both inputs to reduce the spatial dimensions and squeezing them into compact vectors. And next, these vectors are combined and passed through a ReLU function to ensure non-negativity. And through a linear transformation to process the features further, then calculate an attention gate using a sigmoid activation to figure out which feature are most important, and this attention is then applied back to the input features, amplifying the relevant parts while reducing noise. And finally, a second linear transformation produces the deep prediction, which is used to calculate the loss for deep supervision. And just like the diagram shows, how the component in MHEX work together, we can see two inputs and the pooling and the ReLU and the two transformation, and actually the removal of the attention gate sometimes helps to generate a clearer salience map, but will largely lower the confidence of the deep prediction. So with better added on. And then I apply the commutative law of multiplication from linear algebra instead of treating W1 and W2 as separate transformations. I combine them into a single equivalent matrix, and which allow us to analyze it and to reduce uncertainty. So let's try to analyze it. We first form a equivalent matrix, and we split into two parts, the positive part and the negative part. And instead of completely blocking them, blocking the negative part in a hard way, we introduce a scaling factor alpha to weight the negative contribution, because in our observation, sometimes the negative part can actually help to denoise the features. And let's discuss how to analyze features contribution to every neuron. As we talked about earlier, we need to identify the devoted features which focus specifically on certain neurons. And to achieve this, we define the factor called salience sharpness, SS. And the idea is to use this factor to exclude features that are not focusing enough. And next, we form an equivalent matrix and extract positive neurons and positive weights. And then we calculate their sharpness score by normalizing each weight against the sum of all weights. And this gives us a sense of how sharp or how focused a particular feature is. Then we apply a sharpness threshold, and the features with sharpness score below this threshold are excluded. And finally, we do the same thing to negative parts, which I omitted for clarity, and then combine the refined positive and the negative components to calculate the final contribution of the feature. And here is the mathematical derivations for the salience sharpness part. As you can see, it consists of the normalization and the combination part. And to sum up, MHEX is a general module suitable for any network with residual connections, such as ResNet and BERT. And we discussed how MHEX applies in areas like CV and NLP, and how it can improve both performance and explainability. And the three main components of MHEX are attention gate, deep supervision, and the equivalent matrix. And once the fine-tune training is completed, the deep prediction part can be removed. That's exactly what I did in the experiment. And we also explored how to analyze the equivalent matrix to reduce uncertainty and create a clearer salience map. And additionally, there are more fascinating experiments such as how the collaboration of gradients between W1 and W2 can serve as an indicator of the quality of the salience map. And for more comparisons, samples, and quantitative studies and guidelines, please feel free to check out this archive link. And you can access the paper by scanning this QR code, and the Python code on GitHub is coming soon. And you are very welcome to send me an email if you have any questions or would like to discuss further. And thank you all for your attention, and special thanks to Professor Petrulio for his guidance and support. And have a great day, please.
Thank you very much. Thank you very much,
Thank you,
Bob.
Professor.
Just if anybody has questions, let me start with one that is, can you apply this also to graph neural networks, in your opinion?
Yes, I think so. Because graph in GNNs, they are something like nodes, and I think they are very similar in transformers situation, like the tokens. And what we need to do is figure out the residual connection. I think that could be a consideration.
Thank you very much.